Hi, Emily. It's great to have you here. Thank you for joining me, everyone. I want to introduce Professor Emily Riehl, who is the Kelly Miller Professor of Mathematics at Johns Hopkins University. She's an expert in higher category theory, homotopy type theory, and computer formalization. She's the author of several books, including Category Theory in Context, which many people ask me through the channels for suggestions on books, and whenever anybody asks me for a recommendation on category theory, I always recommend your book, which is great. She was an invited speaker at the ICM this year in 2026. She's a member of the Strategic Advisory Board for the MathLib Initiative. She's a member of the Scientific Advisory Board for the Institute of Computer-Aided Reasoning and Mathematics, and many other accolades. So it's great to have you here. Thanks a lot for joining me.
Sure.
And so let's just get into it. Do you currently use AI tools in your math research? And if so, what role are they playing? If not, why not? And do you expect to use them in the future?
Yes. Okay. Right. So I am currently using AI most substantially in computer formalization. Maybe more so in with the aim of understanding AI's capabilities in computer formalization than in necessarily completing computer formalizations that I would have otherwise done by hand. So maybe to back up and explain a little bit, I have a bit of a different perspective on computer formalization than many other mathematicians do. What computer formalization refers to is, typing a proof interactively in a computer proof assistant, and then the computer will provide sort of line by line feedback of the correctness of the proof and things like this. And that's usually done sort of relative to some library of previously defined mathematical concepts. So for most mathematicians, the proof assistant that comes to mind, if any, is something called Lean. And the library that comes to mind is something called MathLib, which is intended as a general purpose library for mathematics, though of course its scope is not currently all of mathematics. But I got interested in computer formalization when I was learning about an alternate approach to the foundations of mathematics called homotopy type theory. And that is also a formal system that could, in principle, be implemented in a computer proof assistant, but is not compatible with the axioms of Lean. So homotopy type theorists instead approach computer formalization through a whole bunch of other proof assistants that you may or may not have heard about. And I think it's relatively underexplored what AI-assisted formalization looks like in that space.
Do you know if AI has made any progress on problems in category theory in particular?
So I also do some formalization in Lean, helping to develop the Lean category theory library, which is already quite well developed, and then their higher category theory library for infinity categories, which is not very well developed. So I'm running a Lean formalization project called the Infinity Cosmos Project, aiming to do some infinity category theory in Lean. And recently we have been seeing some AI-assisted pull requests. That as of a few months ago, AI is finally able to, write some of the code that we need for that library. A few months before this was not at the capability of AI, at least as far as we could tell. I should say that in compared with a pull request submitted by a human who has a bit more experience, the code quality is a bit worse, and so the review process is a bit more difficult. And since I'm pretty time bottlenecked, that's actually been the biggest issue with these new AI generated pull requests is that they're languishing in a review queue for a long time because I don't have as much time to look at them as I would otherwise. And it takes longer to look at them than it would for a human written pull request. And I should say this experience, I think, is pretty similar to the experience of other people who have been using Lean in other areas.
So in general, how do you feel, how do you personally feel about the growing role of AI in mathematics? And has it changed how you think of about what it means to be a mathematician?
So fundamentally, I'd say AI has not changed my view of what it means to be a mathematician, and that's because, like many mathematicians, I was always as interested in understanding why something is true than understanding what is true. Um, so, what AI has been doing, particularly this summer, is expanding sort of what mathematicians know is true. There have been various famous open problems that, in different subfields, that AI has helped find solutions to, particularly if the solution involves constructing an interesting mathematical example that has some particular properties. But even if that example sort of drops out of an AI chat session, there's still work of mathematicians to understand what it means. Where did this counterexample to the Jacobian conjecture come from? Is there another sort of interpretation? And that work seems relatively unchanged from a few months ago, even if the sort of pace of these new examples is increasing dramatically. So.
Have any of these advances that have been announced that are sort of like autonomous um, AI advances, have any of them shocked you and like the depth of it, or anything that you thought it was particularly innovative?
Sure. I should say that none of the announcements from this past summer have been particularly close to my subject area. I think, the mathematicians who worked hard on a problem themselves that has been solved by AI, could have more interesting things to say about this. But I mean, it has certainly adjusted my sense of the capabilities of the frontier models today.
What do you think over the next 2 or 3 years? What role do you expect AI to play in math research?
So I think it's certainly going to transform the way that we learn mathematics. I mean, certainly it's already transforming the way that students learn mathematics or learn kind of any subject area. But researchers too are learning new mathematics all the time. We're trying to keep on top of the literature, trying to read new papers, trying to expand into new areas, and often for a long time, the start for me of learning some mathematics that I don't remember perfectly or is to do a Google search. I would, often use web pages like, Wikipedia or the NLab, which is a collective blog involving category theory and higher category theory as sort of basic references. And, both of those pages are good at documentation. So at the bottom, there will be references to the original literature to get more depth. So I've been using that sort of search process for a while to, learn or recall some mathematics that I've forgotten, in an area where I'm not particularly an expert. And, now, of course, if you do that search, you'll get a large language model results in addition to links to those
Yeah.
particular websites. And it's, depending on what you're looking for, it's very tempting to just talk to the large language model, which is a conversation, maybe like at the level of sort of a non-trustworthy colleague, non-trustworthy because, maybe this is somebody you don't know real well, and so you're not sure whether they have a tendency to bullshit when there's something they don't quite remember accurately.
Do you think that that ability of being more accurate or more trustworthy, is that going to keep increasing to a perfection, or do you think that's just sort of like a process that is never going to get, or at least with this type of technology, do you expect that you'll fully trust these results at some point?
Yeah, I certainly expect accuracy to increase. I mean, like many mathematicians, I've been testing the large language models in my subject areas by asking it questions I know the answer to see if it can get them right. And, we've all observed a lot of improvement over the past several years. Whether it really gets to the point that I will trust it if it's outside my area, I don't know. I mean, I think it kind of depends on how sort of basic the question is. A real sort of frontier level, a research level question, where the answer might not be known to a human mathematician at present. That's the sort of thing that I would prefer to ask AI about in a formal realm. So interacting with an auto formalization agent who's, you know, so the code that's being produced is checked by a proof assistant, which I do by and large trust, as opposed to just sort of in the natural language. But if you're just doing a literature search thing, like say, I've forgotten everything that I once knew about differential geometry, remind me what X means, I think probably at this stage a lot of that is pretty accurate.
I have a very basic concept of how lean works, how
Mhm.
it's built.
Sure.
But so recently there was some bug that was exploited in lean
Mhm.
to prove the Collatz conjecture.
Mhm.
And after that, there were some like big conversation about like what happened and how to patch it. But then there were other people, like I think Talia Ringer was
Mhm.
also talking about the type theory that is behind the sort of like the foundations of lean.
Mhm.
I was wondering if you could try to explain what happened and what do you see that is happening there.
Sure. So I am not an expert in computer proof assistant architecture, so it's
Right.
possible that everything I will say is sort of a bit wrong. But let me say what I do understand. Um, uh, a computer proof assistant implements some sort of formal system for mathematics, so it knows the rule of some foundation for mathematics. Typically, that foundation is some sort of type theory or dependent type theory. That's the case for Lean and also for Agda and Rock, which are two proof assistants used by homotopy type theorists. The idea is sort of at some level, you have to write a program explaining the sort of foundational rules of the type theory. This is something called the kernel of the proof assistant, and that's kind of a bit that needs to be trusted. So maybe it could be validated by trying to check that code using a separate proof assistant, some sort of relative consistency check. But the idea is that the sort of the formal system, the formal code that is really verifying the proofs down to the basic rules of the formal system is sort of a relatively small piece of the kernel. Various proof assistants will, one design choice made by Lean in particular and reflected, I think, in the name is that the kernel is sort of relatively small. So even if it hasn't entirely been formally validated, there is a sort of Lean for Lean project being led by Mario Carneiro and to sort of give some sort of relative consistency check of the Lean kernel. That is not complete, but I think it is still sort of relatively trusted in that proof assistant at least. So I think what specifically happened in this case was about the other layers of the proof assistant that are built on top of the kernel, because if the kernel is all there is, then the users of the proof assistant would have to essentially write in machine code. And instead, they're writing in sort of a vernaculator that is then elaborated into this machine code. And my understanding is this specific bug involved those other layers and also this capacity of Lean for what's called metaprogramming, which is to also write sort of Lean programs in Lean. And I think a lot of concerns about, sort of AI's cheating Lean are kind of about those more advanced layers, which I don't understand particularly well. But what Talia's point is that if we, again, my perspective is that we don't care just about one proof assistant. We might care about lots of different proof assistants because of different mathematicians have different approaches to the foundations of mathematics, different desiderata when working in with a formal system. And lots of other proof assistants like Agda in particular are somewhat experimental in the terms of the type theory that they implement. One thing that's nice in the Agda proof assistant is that the user can sort of at the top of the file indicate exactly which type theory they want to work with. They can alter the rules for identity types. They can add various bells and features. They can add certain modalities and so on and so forth. And that flexibility is great for users, but also means that there are a lot more theoretical challenges to understand exactly how these different flavors of type theory interact. And I think this area is understudied. I mean, for one thing, most mathematicians know essentially nothing about type theory, and also sort of new type theories are being developed all the time. And so the sort of foundational work that needs to be done is quite large. So,
What should be the process for that formalization? I mean, my understanding is that when a paper is formalized in Lean checks that that formalization compiles,
mhm.
but then how do you check that it's compiling what you think it's actually proving?
Right. So what Lean is doing when it's checking the logic of a proof is something called type checking. So in the foundations of type theory, there are two kind of primitive notions. There are things called types, and there are things that are sometimes called terms, but I'll call them elements, which belong to types. And sort of unlike set theory, an element only ever belongs to one type. So there's a zero, which is a natural number belonging to the natural numbers type, and there's a different zero that's a real number. And for instance, and this sort of precision is partially why it's easier to communicate mathematics with a computer using type theory as opposed to set theory or another approach to the foundations of mathematics. So, so another feature of type theory that takes some getting used to, this is sometimes called the Curry-Howard correspondence or propositions as types, is that when you state a mathematical theorem in type theory, what you do is you form a type that encodes the statement of the theorem. So the type might have the form, assuming X is true and Y is true and Z is true, then there exists an object B satisfying properties, blah, blah, blah. So that specification, that's theorem statement, is the name of a type. When a user types a proof, that's intended to be an element of the type. And so now the task for the proof assistant is to verify that the element that the user sort of wrote in the code is in fact an element of the type that states the theorem. And there are sort of inductively specified rules for producing new elements from other elements. So you can essentially just inspect the structure of the element that the user typed into the program and inductively check that it belongs to the given type. So there are rules that for functions, elements of functions types. They're used for rules for sort of elements of product types. There are rules for proofs of the universal and existential quantifiers and so on. So it's a pretty mechanical procedure that can be approached algorithmically, and that's what's programmed into the proof assistant. That is what they are doing. But all it ever verifies is that the proof is in fact a proof of the theorem that was stated. The proof assistant does not automatically check that the stated theorem is the theorem that the user intended.
Right.
That's a process that has not been automated presently.
And is there sort of like a something in the works, or like what would be the a way to sort of like verify that there is a match?
Right. I mean, if we're trying to do that automatically, sort of the ideas are not perfect ideas. One would involve kind of translating out of one proof assistant into another proof assistant or translating back into natural language. If you start with a natural language theorem statement, it becomes a formal theorem statement. An LLM turns it into a formal theorem statement, and then an LLM turns it back into a natural language statement. You can ask whether those are the same statements or whether they're different.
Right.
That's one idea. Another idea is to what's particularly difficult is actually the definitions, whether, because mathematical definitions can be quite complicated and it's easy to make mistakes, even, innocent mistakes. But if you've defined, something like a group, you might try to show that, permutations give an example of a group. And if you're successful at that, that gives you some evidence. It doesn't prove that the definition of group was correct, but it gives you some evidence. And you could try to prove that, if your group is finite and then you have any element of that group, then the order of the element divides the order of the group. And if you're able to prove that, that's giving some further evidence that all your definitions are correct. Though, again, it's not a proof that the definition is correct. And so that's another idea, is to sort of develop this infrastructure, building examples, sort of checking the desired properties to justify definitions.
Yeah.
But
I
I
mean,
think this is an open problem in general to see if this is possible to automate.
yeah, one of my concerns is that OpenAI, Anthropic, they release these like flashy announcement and they say, and here we have a Lean certificate for
Mhm.
it. And that seems to, for many people, they take that like, okay, it's proved, and now we can sort of like assume that it's true without really going into that Lean certificate and see like what is it actually proving.
Yeah, I mean
Right.
the lean experts sort of understand exactly what is implied by this lean certificate. I still think it is better that they exist than that they don't. But because it is sort of an artifact that anybody in principle can sort of interact with and start to analyze in the ways that we're discussing. I think an interesting thing though is there are only certain areas of mathematics where it would be possible to su produce a lean certificate. There are, if your AI generated proof is, something involving homological mirror symmetry or something involving the Langlands program, that the statements of theorems in that area involve definitions that are too complicated and are not currently in MATLAB. Um, so if anybody gave a lean certificate for that, I would be extremely suspicious that it was correct.
Right. I know. I absolutely think that it's definitely a right step that they are at least providing some sort of Lean certificate. I'm more worried about the general public that
Mm.
see that as like, okay, they have proved it and that's it. Um,
Right, but
but
I think this kind of brings back to our earlier discussion that, even with AI, sort of individual human expertise is quite valuable. So the people who are best able to understand what these Lean certificates mean are the humans who have developed expertise in computer formalization and Lean
right.
using MATLAB. So even though AI can produce Lean code now, there's still reason for humans to develop that expertise. So,
Changing to the topic of actual education.
mhm.
So, should mathematics education at the undergraduate or graduate level change in response to current future AI tools? And if so, how do you have ideas? Have you have thoughts about this?
Yeah, I think certainly. So, for example, at the undergraduate level, just a little bit before, ChatGPT was any good at math or any good at arithmetic, I was teaching the computational linear algebra course. And, one of the standard things covered in that course is these algorithms for taking a matrix and converting it into row-reduced echelon form. So, a large language model the semester I was teaching was not able to do that calculation, but there are, of course, other computer tools that could have done that calculation. So I was mindful that when I was assigning homework exercises to my students, that the point of the homework was to understand, what does this algorithm mean? When is it, what sort of information does it give you? When is it the right way to solve a problem by starting to do this algorithm? How does the sort of image of a matrix compare with the image of its row reduced echelon form? What about the kernel? Sort of more conceptual questions like that were my focus already. Because a human would never need to write that algorithm out themselves because there are computer tools for this. So um, now today, if I were teaching that course, I would have to take things a step further because, an AI could answer those more conceptual questions about these matrices as well, which was not the case when I taught this course more recently. Um, so, but the fundamental goal of that my students are the ones that have this understanding, not that the internet has this understanding, would be unchanged. So what that means in practice is that, in my department, we're changing the nature of assessments in these courses, sort of moving more work from sort of homework into in-class work, where the instructor's there on hand to engage directly with the student, sort of give real-time feedback. That's sort of the sort of platonic ideal mode of teaching, and is relatively unaffected by AI. So that's sort of what we're doing at the undergraduate level. I think at the graduate level, things are a little bit more complicated. One difference between sort of, 'cause, mathematics graduate students is that they typically chose to be there. They're in the classroom because they really are trying to sort of learn new mathematics. So we're perhaps a little bit less concerned with students asking AI to solve problem sets at that level. But nevertheless, these AI tools are going to affect research practices. And, a conversation that I've been having with colleagues is that, perhaps, more of our focus should actually be on exposition, where, orally as much as written, if a student can explain a concept at the board, and provide useful examples and understand how it connects to concepts in other fields, that's really the sort of valuable understanding that we're hoping our students will go away with. And maybe the best way to demonstrate that will be orally, sort of in a sort of human to human conversation as opposed to sort of in written form as it has been in the past. So.
Do you also see some value in teaching students, the undergrads and the graduate students, how to effectively use these AI tools in basic mathematics and research mathematics? At the same time, like I understand, like you want them to be doing the important thinking in the classroom.
Yes,
Um,
I think so. I mean, I think, students come and, non-students also come with a wide variety of opinions about AI.
mhm.
Some people are extremely anti-AI, and I think, an assignment that would force students to use AI is maybe something I would hesitate to give these days because, there are folks who really would rather not do that. However, I think it is useful for everybody to have some sort of understanding of the current capabilities and limitations of AI, whether or not they're using it to help them in their own work in any case. But a student who wants to learn math by reading books, there are plenty of wonderful books that they can learn math. They don't need to learn math using AI in any way. But I think it's useful for folks to know sort of what AI can and can't do because, we're in a society with others who are using these tools. And, that's just an important part of, I'd say, literacy these days.
So, what advice would you give to students or early career mathematicians thinking about a career in mathematics in light of the recent advances of AI?
Sure. So, yeah, I could think, again, one part of the advice would be to be mindful of what AI can and can't do. There's, particularly in certain areas, if you're working in combinatorics, it used to be that you could sort of earn a reputation for solving a certain type of problem in a clever way. And if AI is capable of solving those problems in that clever way, that won't benefit a human who is solving the problems, with or without AI in the same way as it would have before. So I think being aware of capabilities of the models in your areas is an important thing for aspiring researchers. Um, I think similarly, simultaneously, that awareness will help you focus on areas where you can add value. So, I mean, for example, speaking for myself, I've always been particularly interested in expository writing. I felt like this is an area that I can add value. And, my goal in writing is not just to sort of write true facts down on the page, but write them in a way that will help somebody who doesn't know them already learn them. So explain some intuitions, find some motivating examples, explain things that might be confusing, because it's easy once you've understood something to just sort of spit it out on the page without the surrounding context of all the reasons that this concept is confusing. And that work still involves a lot of creativity. Uh, still, I think gives a value add over, sort of the AI generated version of similar content, which I would say is a bit more generic. And so that's one area that, human mathematician can add value. But I think there are other areas, again, involving, finding creative applications of existing mathematics, new perspectives on existing mathematics, ways to explain mathematics to new audiences. So that's some expertise I might try to develop. So,
Um, I think during when you were moderating one of the panels at the ICM, you uh, advertised this newer journal, Essential Number Theory,
mhm.
which I thought it's a great idea, and I hope that there's also appear some other ideas like that show up in other areas.
Right. And
Uh,
for those who don't know this, the point of essential number theory is that it would, among other things, contain like the canonical version of a sort of standard technique in the field. I think in many areas there are these sort of styles of proof or modes of reasoning that like all of the experts know, but they don't really appear explained in the literature anywhere because it's sort of things that with sufficient experience you can learn sort of between the literature. So the idea is that anybody who has a sort of clear understanding of what it is that somebody might want to know, whether or not they were the ones who originally discovered this type of mathematics, could write down sort of the definitive exposition to help others in the field learn these techniques. And this is meant to be a sort of prestigious publication venue for these very valuable contributions to the literature. Maybe just one final takeaway to young people. I think if you're kind of following this AI for math stuff online, you're getting a pretty flattened perspective of what math is and what the future might entail. But firstly, the mathematical universe is enormous and kind of growing all the time. So even if AI helps us solve a lot of problems, and it certainly has helped us solve a lot of problems this summer, there are sort of innumerably more problems that AI has not yet helped us solve and might not be able to help us solve. And even as these tools get better, there are going to be important roles for humans in making sense of it all. There's sort of too much math out there to fit in any person's brain, but hopefully collectively, all of our brains can span the most important concepts and also help distill and simplify them down so that, folks coming up in the next generation will have an easier time learning of these latest advances. But in order for that to happen, we need, not just the initial moment of the discovery, but the kind of understanding of the discovery, the improvement of the discovery, adding better references, better citations, understanding the historical lineage, distilling it down to the sort of reusable core, the new abstract concepts or the new proof techniques, and then the communication of this to a lot of audiences. So there's plenty of work to do for mathematicians today, and I'm confident that'll be true in the future.
I get random comments in my videos saying like, is it worth doing a PhD in mathematics in 2026?
Yeah.
What do you think?
Yeah, I would say absolutely. It's, one thing that I've heard folks say, and I think might be exciting, is that, uh, different people might be drawn to the mathematical community in the future. It's likely that it, won't be so important anymore who is the first person who proved X because, ownership over proofs might become a bit more complicated if, AI tools are involved in those proofs. But again, we will still need people to understand the proofs and communicate the proofs and, dream up new conjectures and dream up new theories. And if these things appeal to you, as uh, mathematics is a collective and we could always use more members. So,
Well,
yeah.
thank you very much. This has been great. Thanks a lot for sharing all these thoughts. So yeah, thank you.
Sure. Take care. Yeah.